Today, I will be discussing with you another topic in machine elements. But before that, let us have a quick review of our previous topics during the midterm weeks. So we tackled about the fundamental concepts in machine elements, vector operation, motion and machinery, instant center, velocity analysis, and acceleration analysis. Today, we will be discussing about CAM, so the CAM design. So previously we discussed majority of the time about linkages, but our focus will be another machine element which is the CAM, in particular the design of CAM profile. At the end of this lesson, you should be able to identify the different terminologies in CAM design, create displacement diagram for CAM follower undergoing uniform velocity, simple harmonic motion, and uniform acceleration and retardation, and sketch the gum profile of radial cams for knife edge and roller follower. So this will be the outline of my presentation. So let's start first with the various cam terminology. A cam is a rotating element which gives reciprocating or oscillating motion to another element known as the follower. Cam and the follower have aligned contact and constitute a higher pairs. Cam are usually rotated at uniform speed by a shaft while the follower motion is predetermined and will be according to the shape of the cam. As you can see here in the image, we have the cam, which dictates the motion of the follower, and the follower. The cam's rotation is dictated by the rotation of the shaft, while the follower depends on the profile of the cam. The cam and follower are one of the simplest and one of the most important mechanism in modern machinery. Some of the applications are the inlet and outlet valves of internal combustion engines, automatic attachment of machineries, paper cutting machines, spinning and weaving textile machineries, fed mechanism of automatic lathes, among others. Compared to linkages, cams are easier to design to give a specific output function, but they are much more difficult and expensive to make than a linkage. Cams are a form of degenerative four-bar linkage in which the coupler link has been replaced by a half joint. So as you can see here, an oscillating cam follower has an effective pin-jointed four-bar equivalent. A translating cam follower, on the other hand, has an effective 4-bar slider crank equivalent. Some of commercially available roller followers are shown. We also have commercially available cams and motorcycle camshaft. So this is how they look like in actual practice. There are different classifications of cams. The first one is the radial or disc cam. The follower reciprocates or oscillates in a direction perpendicular to the cam axis. Take note of the term perpendicular. On the other hand, cylindrical cam, the follower rides in a groove at its cylindrical surface, and the follower reciprocates or oscillates in a direction parallel to the cam axis. So the difference between the two is the motion of the follower, whether it is perpendicular, so it's called radial, and if it is parallel, they are called cylindrical cam. So you can see here the radial cam, and then we have a cylindrical cam. The radial or disc cam mechanisms are shown here, for example, for an internal combustion engine, especially in the valves. So in order to open and close the valves, the internal combustion engine uses cams. So these are examples of radial or disc cams applied in internal combustion engines. Cylindrical cams, on the other hand, are also widely used, as you can see here in this animation. On the other hand, followers can also be classified according to surface and contact, which can either be knife edge follower, roller follower, flat face or mushroom follower, and spherical face follower. They can also be classified according to the motion of the follower, which can be reciprocating or translating, or oscillating or rotating follower. They can also be classified as either radial follower or offset follower based on the path of motion of the follower. So let us first examine the classification of followers by surface contact. So the first classification is the knife edge follower. So as you can see here in the diagram, the contacting end of the follower has a sharp knife edge. Seldom used in practice because the small area of the contacting surface results in excessive wear. A considerable side thrust exists between the follower and the guide when you use knife edge follower. The roller follower, on the other hand, the contacting end of the follower is a roller. The rate of wear is greatly reduced when you use the roller follower. The side thrust also exists between the follower and the guide, as you can see. The roller followers are extensively used where more space is available. Then we also have the flat face or mushroom follower. The contacting end of the follower is perfectly flat face. The side thrust between the follower and the guide is much reduced. The wear may be reduced by offsetting the axis of the follower. It is generally used where space is limited. When the flat face follower is circular, it is then called a mushroom follower. Finally, we have the spherical follower. The contacting end of the follower is of spherical shape. The flat end of the flat face follower is machined to a spherical shape to minimize stresses. Now that we learned the classification of followers based on surface contact, we can also classify them based on the follower motion. The first classification is the reciprocating or translating follower. Here, the follower reciprocates and guides as the cam rotates uniformly. For oscillating or rotating follower, on the other hand, the uniform rotary motion of the cam is converted into predetermined oscillatory motion of the follower. The third classification is based on the path of motion of the follower. The first one is a radial follower. Here, the motion of the follower is along an axis passing through the center of the cam. So as you can see in the illustration, the axis of the follower and the cam coincides. On the other hand, for offset follower, the motion of the follower is along an axis away from the axis of the cam center. So as you can see there is an offset between the center of the follower as well as the center of the cam's rotation. So this is then called offset follower. In all cases, the follower must be constrained to follow the cam. This may be done by springs, gravity, or hydraulic means. In actual practice, radial cams are widely used, therefore our discussion will only be focused on radial cams. Here are some radial cams terminologies. It is important to learn the terminology so that later on, when we have the designs of cams, it will be easier for us to define each of the different parts. The first is the base circle. The base circle is the smallest circle that can be drawn to the cam profile. The trace point, on the other hand, is the reference point on the follower. It is used to generate the pitch curve. In case of the knife edge follower, the knife edge represents the trace point, and the pitch curve corresponds to the cam profile. On the other hand, for roller follower, the center of the roller represents the trace point, and the pitch curve is not the cam profile. So we will be able to appreciate this trace point and pitch curve later on. So the base circle is shown here. So it is the smallest circle that can be drawn. And we also have the trace points. So that the numbers 1 to 10 along that are the trace points. So they are generated along the pitch curve. We also have the pressure angle. This is the maximum angle. This is the angle between the direction of the follower motion and normal to the pitch curve. This angle is very important in designing a cam profile because if the pressure angle is too large, a reciprocating follower will jam in its bearings. The pitch point, on the other hand, is the point on the pitch curve having the maximum pressure angle. So here we can see the pressure angle. It is the angle between these two red lines here. So this first line here is the follower motion because it will be uh, translating in that direction. On the other hand, this line here represents the normal to the pitch curve or perpendicular to the pitch curve. So the angle between them is the pressure angle, and this portion here is the maximum pressure angle. The point on the pitch curve with the maximum pressure angle is the pitch point, as you can see here. So this point is the pitch point. We also have another pitch point here. Next, we have the pitch circle. The pitch circle is a circle drawn from the center of the cam through the pitch points. The pitch curve, on the other hand, is the curve generated by the trace point as the follower moves relative to the cam. So the pitch circles are shown here. So the circle that can be drawn from the center of the cam through the pitch point is what we call the pitch circle. The pitch curve is the curve that can be generated if you trace the trace points as the follower moves around the cam. The prime circle, on the other hand, is the smallest circle that can be drawn from the center of the cam and tangent to the pitch curve. For a knife edge and a flat face follower, the prime circle and the base circle are identical. For a roller follower, the prime circle is larger than the base circle by the radius of the follower. The lift or stroke, on the other hand, is the maximum travel of the follower from its lowest position to the topmost position. So here we can show the prime circle. It is for this roller follower, the prime circle is larger than the base circle by the radius of the roller. So you can see here, this is our base circle. The prime circle has a difference in terms of the radius of the roller, as you can see. So the lift or stroke, on the other hand, is shown here. So this is the maximum travel of the follower from its lowest position to its maximum position as it translates because of the rotation of the cam. So now that we learned the different cam terminologies, let us deal with motion synthesis. So for motion of the follower, it can either be uniform velocity, simple harmonic motion, and uniformly accelerated and retardation. Some of the terms that will help us in motion synthesis are the displacement diagram, which is the plot of the linear displacement of follower versus the angular displacement of the cam for one full rotation of the cam. In the displacement diagram, we can see the period, which is part of the cam cycle and includes the rise, which is the upward motion of the follower, fall, the downward motion of the follower, and dwell, the stationary position of the follower. Now that we know the different terminologies, let us try to examine the cam profiles. For uniform velocity, this is the displacement diagram. So in drawing the cam profile, it is very important for beginners to draw the displacement diagram because it will help us in drawing the cam profile. So for uniform velocity, the rise and the return, or the rise and the fall, will be represented by a straight line from the initial point to the final point. So as you can see here, there is a rise from A to B, and then we have a dwell from B to C, and then we have a return from C to D, and another dwell from D to E. So all in all, this totals one revolution of the cam. or 360 degrees. So the distance from point A to B1 or CC1 or BB1 is what we call the stroke. So let us try to apply uniform velocity in drawing the cam profile of this given. So we consider the cam design, critical extreme position specifications such as rise, uniform velocity 1 inch for 180 degrees, and fall, uniform velocity 1 inch for 180 degrees. The cam will rotate counterclockwise as you can see in the drawing. Here we will use the knife edge as an example. So first, we should draw the displacement diagram. As you can see here, we are given with two CEP specification, rise and fall. Both are uniform velocity. The stroke is 1 inch of the same angle 180 degrees. So all in all, it will total 360 degrees. So we will draw first these angles along the x-axis of our displacement diagram. So we have 180 degrees and 360 degrees. So the first half represent the first CEP specification, which is the rise, and the second one would represent the fall. So we will also note the other angles: 0 degrees, 45 degrees, 90 degrees, 135 degrees, and so on and so forth. The choice of the angle is dependent on the designer, but it is best to have as smaller angle as possible. So for the sake of this example, we will use 45 degrees so that it will be easier for us, because this is just an example. But when you design, you have to choose a smaller angle that will be convenient also for you. So first, we will draw the rise uniform velocity for 180 degrees. So if this is 1 inch, therefore from 0 degrees, it will reach 1 inch in stroke by the end of 180 degrees for uniform velocity. So as you can see here, the fall on the other hand is represented by this straight red line sloping downward from 180 to 360 degrees. So this completes the whole cycle of this given cam follower. So now that we have the displacement diagram, we will then plot it. We can do that by noting some points that intersects this red line to the different angles. So for 0 degrees, for 45 degrees, 90 degrees, 135 degrees, and 180 degrees. So these are the intersection of these divisions of angles here, the displacement, as well as this motion, as you can see. And we are going to project this in our follower. So by drawing horizontal line through the follower. So we were able to draw the displacement diagram for half of the cycle. We will also do the same in the camshaft. So in the camshaft, we will also draw the same number of angles and the same divisions. So here we have 4 divisions, 45, 90, 135, and 180 for the first half, and another 4 for the second half of this CEP specification. So we will divide the camshaft by 45 degrees. So we have 0 degrees, we have 45, 90, 135, 180, so on and so forth until 360. So that means that it would completely have one complete revolution. After that, we are going to draw a concentric circle. It means that the center of the circle is also the center of the camshaft to or through the knife edge, as you can see here. And then we're going to mark that point later on. We will also draw another concentric circle to the second horizontal line, as you can see here. This is the projection of the 45 degrees, and another circle projecting 90 degrees, as you can see. Another circle for 135 degrees, and finally another circle for 180 degrees. After that, we're going to locate the trace point. So for knife edge follower, we know that the trace point is the edge of the knife. So this would be the trace point. So meaning those points that will be touched by this knife would be the trace point. So for at 0 degrees, the trace point is shown in the red dot here. So this represents point A. You can arbitrarily assign letters. At this is 0 degrees. This means that it is at the initial position. For 45 degrees, so as you can see, since this shaft rotates counterclockwise, the right side of this uh, profile will be the first that will be touched by this knife edge. So that's why we will draw the next point towards the right side, or we will draw it opposing the counterclockwise direction or the clockwise direction. So if the direction is counterclockwise, we will draw the trace points first clockwise or the opposite side. So for 45 degrees, it should touch the 45 degrees line here and also the circle for 45 degrees, and this is this point. So that point represents point B during the 45 degrees rotation. So it means that at that point, the follower will already rise in that position. And then we will also have for 90 degrees and its intersection with the 90-degree circle. Same also with 135 and finally for 180. So we're able to draw the trace points for the first half of this cam design CEP specification. As you can see, there is a symmetry between the first part of this displacement diagram and the second part. That means that also here in our cam profile, we will just have a mirror or a symmetry. So that's the reason why we did not draw this part any longer, because we will just use the pitch curve that we can generate from the trace points. So if you're going to connect these dotted red lines using a French curve or a smoother curve so that it will be perfect, we will generate almost like this kind of profile. So this represents now the cam profile. So as you can see, for a knife edge, the cam profile is the same as the pitch curve. And since they have symmetry on the second part, we will just project this to the other half to complete the 360-degree rotation of the cam. So therefore, we will have this cam profile in order to achieve this motion that we needed. So take note that the input in the design is the motion required, and the output is the cam profile design, among others. So that is how we use the knife edge in drawing the cam profile, and also how to draw the displacement diagram for uniform velocity. Now we can move to the second motion of the follower, which is the simple harmonic motion. For the simple harmonic motion, this is how it would look like. So the curve now will look like this for the rise, and then we have the dwell, and then we have the fall, and then we have another dwell to complete the 360 degrees rotation of the cam. In order to aid in drawing the simple harmonic motion, we will use a semicircle that will give us later on the position or the stroke of the follower. So some equations that might help us in the future in solving the time required for the outstroke of the follower, the maximum velocity and maximum acceleration is shown here in this line. But for the sake of discussion, we will not tackle so much on this. So let us use the simple harmonic motion in designing this cam follower. So we have here a camshaft that rotates clockwise. So as you can see by this arrow, it will rotate clockwise, and we will design the cam for the CEP specification with having a rise of simple harmonic motion 1 inch for 180 degrees, or half of the rotation of the cam, dwell for 90 degrees, and another 90 degree for the fall with a uniform velocity 1 inch. As you can see, it would total 360 degrees. It is different from the first example because here we will use the roller follower, as you can see here. But we have the same first step. We will draw first the displacement diagram. So as you can see here, unlike the knife edge follower, the bottom part of our displacement diagram axis is the center of the follower, because the center of the roller follower is our trace point. So it would give us the trace point, not the lower part here. So that's why it is drawn here, so that we can measure 1 inch from that, and that would be the stroke of the roller follower when the cam rotates. After that, we're going to locate the 180 degrees to represent the rise of simple harmonic motion, and also to complete the cycle 360 degrees. And then we'll also draw the other angles such as 0 degrees among others in order for us to easily locate the different points. So for this example, since we have 90 degree and it would be convenient to divide it by 30, so that's why I use that. So we have 0, 30, 60, 90, 120, 150, 180, and so on and so forth. So let's start first with the first CEP specification, which is a rise of simple harmonic motion 1 inch for 180 degrees. This means that the follower will rise from 0 inch in a 0 degrees position, and once it rotated 180 degrees, it will be at 1 inch already in its translation. So to aid us in drawing the simple harmonic motion, the rise of simple harmonic motion, we will use the semicircle here. So the technique is to divide the semicircle in the same angle that we divide the portion that contains the simple harmonic motion. So as you can see here, since we have a simple harmonic motions of 0 to 180, we'll also divide this semicircle with these divisions that we can see here. We have 1, 2, 3, 4, 5, 6 division. So we'll also divide this semicircle with 6 divisions from the center with a uniform interval of 30 degrees. So we have here the first 30, the second 30, the third 30, the fourth, the fifth, and to complete is the sixth one here. So these divisions would represent this division that you can also see here in the axis. Then after that, we are going to draw a horizontal line from the intersection of this division to the circumference of this semicircle. So the intersection of this horizontal line and this vertical line would represent the stroke or the displacement of the follower. So as you can see here, we have from 0, it is still in the bottom position. Once it rotated 30 degrees, it is now rising by this distance here. At 60 degrees rotation, it will be as high as this, and so on and so forth until it reaches the maximum 1 inch at 180 degrees. So this now represents the simple harmonic motion, wherein it would reach 1 inch by the end of 180 degrees. For the second part, we are going to have dwell of 90 degrees. So that means that after 180, by adding 90 to that, it will have the same position. It will stay at that position, meaning it will be at the 1 inch position from 180 to 270, because that's 180 plus 90. So there's a dwell from 180 to 270 on the second part of this CEP specification. And then finally, on the last part, we have a fall, which is uniform velocity. That's why it's a straight line, as you can see based on the previous example. 1 inch for 90 degrees, that means that it would reach the original position at the 0 inch by the end of the 360 degree rotation. Then we are going to trace also the different points that would intersect this line, as you can see. So for 210, 240, 270, it would touch this line here, and for 300 it would touch these lines. As you can see here, this orange line is the horizontal line that represents the intersection of 300 and also for 330. So it intersects the 330 as well as the curve. So I noted it in orange so that it will not confuse us later on in drawing the cam profile. So this now represents the complete displacement diagram for the CEP specification. So after drawing that, we are also going to divide the cam into the same divisions that we have here in our displacement diagram, which is by 30. So we'll divide it by 30 starting on the left side, because now our camshaft would rotate clockwise. It would mean that our first trace point would be on the left side. So we draw by 30 to complete the whole 360. After that, we're going to draw now the concentric circles. So beginning with the 0 degrees. So take note that the trace point is the center, that's why it is at that point. So that is our first point, trace point. The second trace point, which is at 30, is the intersection of this horizontal line to the follower. We're going to draw a semicircle until that point, concentric with the first circle. So the intersection of that circle and our 30 degrees here will be the second trace point. Now for the 60 degrees, we have this horizontal line intersection, and the point that would represent that is this point here. So we'll also do the same for the other points, the 90 degrees, for 120 degrees, for 150 degrees, and finally for 180 degrees. So we're able to draw now the trace point, locate the trace points for half of the revolution. So now we'll have the dwell. So for the dwell, it means that it would stay on that circle from 180 to 270. So that means from 180 to 270 rotation will just be remaining on that position. So that's why we have these points. As you can see now here, for 210 we have this point, for 240 we have that point, and finally for 270 we have that point. So they are located on the same circle from 180, since there's a dwell after 180 to 270. So that represents the second CUP specification. And finally, for the fall of uniform velocity, we're going to use this orange line intersection with the follower. So the first one is for 300, and the intersection is that point. And then for 330, which is represented by that point. So we're able to draw locate the trace points for this roller follower. So after that, since the trace points of the roller follower is not the same as the cam profile, the reason for that is because it is not the center that would touch the cam, but it is the bottom part. So as a consequence of that, we're going to draw the same roller in every points that we generated, as shown here. So these circles has the same radius as this circle, and the intersection of the bottom of this circle would represent now the cam profile. So we have the cam profile. If we're going to use French curve, the curve will be smoother than this one. So make sure to have a smoother cam profile when you draw it, especially on paper. You can use French curve to make it better than this. But for the sake of instruction, this is how to draw the cam profile if you have simple harmonic motion and combining it with well and other motion for a roller follower. Finally, we have uniform acceleration and retardation. For uniform acceleration and retardation, it means that it will have a uniform acceleration and it will have a uniform retardation or deceleration. So you can see here, the first part represents our rise, and then we have a dwell and the fall, as you can see. So we are going to illustrate how to do this. But for this example, we will have an offset follower. If you can still recall, the axis of the offset follower is not coinciding with the axis of the camshaft center. That's why it looks like this. So the design now will be different, but we'll still have some processes the same. For the sake of simplicity, I will illustrate this using the knife edge. And we will have the rise of uniform acceleration 1 inch for 180 degrees to illustrate the third motion. And the second part is the form uniform velocity 1 inch for 180 degrees to complete the whole rotation of this design. The rotation of the cam is counterclockwise, as you can see. So the first step is to draw the displacement diagram. And then we're going to measure 1 inch from the bottom of the knife to the top. After that, we're going to locate the different angles. We can divide it at a convenient angle that we'd like to. As you can see here, there are 3 dotted lines at 90 degrees. So why is it that there is 3 dotted lines there? So as you can see, for this CEP specification, we have a rise uniform acceleration for 180 degrees. That's why we draw first that portion here, as you can see. These dotted lines here represents the divisions that we will have for this part of the specification. Since we have 4 divisions, which are 45, 90, 135, and 180, we'll also divide the middle division with the same number of divisions with an equal length. So the distances of these 3 points are the same, and it divides this line here into 4 equal parts. Why is it that the 90 is chosen? So you will choose the division which is in the middle. So since 90 is in the middle of this other divisions here, so that's why we draw these points here. And then after that, we're going to draw a line that would connect this dotted line for the bottom part to the 0 and the upper half to the 180. As you can see here, we'll connect it to 0, the middle lower part, and for the middle upper part, we'll connect it to 180. And to locate the points, we are going to find the intersection of the divisions with these lines. So for 45, the intersection of 45 with the first line here that represents also the 45 is this point. For 90 degrees, it is this point in the center. For 135, this is represented by this third dotted line, and the intersection is that point. And we will also have intersection for 180 as well as for 0, as you can see there. Then after that, we're going to draw the horizontal lines so that it will be used later on when drawing the concentric circles for the cam profile. So that is the displacement diagram for the rise uniform acceleration 1 inch for 180 degrees. For the second half, this is how it would look like, because it will just be fall. And we'll also have here the different divisions, as you can see. We'll also project these intersections to our cam follower shown by the orange line so that it will not be confusing for us to draw the concentric circles later on. So the difference in the design of offset and radial follower is that now our axis has also rotated. What do we mean by that? As you can see a while ago, the XY plane is just at its normal condition, but here it will be rotated. This time the y-axis will be the connection between the center of the camshaft and the edge of the knife. So this is represented by this line. So this is now the y-axis. You're going to draw a line connecting the center of the camshaft to the edge of the knife, so to represent the y-axis. And for the x-axis, it would always be perpendicular to the y-axis passing through the camshaft. So these two lines are perpendicular. So this is now our new axis. It means that if we're going to rotate this follower into this line, we can draw the cam profile. How do we do that? It will be easier by drawing also the concentric circle that would pass through this horizontal line intersection with this axis, but this time our circle should be concentric with respect to the new xy plane. So for the first point, before that, we're going to draw the different angles from 0 to 360 degrees. Now the measurement of the angles has also been rotated. So the reference for the first 45 is this red line here. So this, we measured it 45 degrees, another 45 degrees here, another 45 to complete the 360 degrees. So it is not the original xy plane. So the new basis is the new xy plane. So as you can see, then we're going to draw the first concentric circle that would touch the knife edge, and then we can locate already the first or initial point. So that is for 0 degrees. For 45 degrees, we're going to draw the concentric circle that would touch the horizontal line for 45 degrees, as you can to this follower axis. And then we would locate the intersection of that with the 45 degrees here. And then we have for 90 degrees, and then we have for 135 degrees, and finally for 180 degrees. So we're able to draw the trace points, locate the trace points for the uniform acceleration. For the heft of the part, it will be the same procedure. So we're going to draw the concentric circles and locate it with the corresponding angles for 225 and also for 270, and then we have for 325, and finally for 360 it will be back on its initial position. So these now are our trace points, and the intersection when you draw the curve is the cam profile, because for the knife edge it will just be the same. So we are going to draw that. So this would represent now the cam profile for this offset cam follower mechanism using knife edge and having rise of uniform acceleration, fall of uniform velocity, rotating counterclockwise. So that's how we can draw the displacement diagram for uniform acceleration and retardation, and also how we can draw using an offset follower. So I hope that you can also do it independently when we have, for example, a roller follower having an offset and a different combination. So try to practice it more. If you are not yet contented of this video presentation, I would require you to watch the following video by clicking the link found in our handout. So this video discusses in details the creation of the cam profile for knife edge follower using uniform velocity and simple harmonic motion, as well as for the cam profile with uniform acceleration and retardation. Thank you for listening. See you in our class